that are probably going to be taking advantage of looking at this. So first thing, test will be Thursday. It shouldn't be a really huge deal. It's going to be dealing with chapters 1 through 4. And it will be specifically targeting towards the reading and the lecture notes. So nothing associated with any of the laboratory types of stuff, okay? So no software issues, nothing like that. So you won't be expected to do any of that. It will be open note, open book, okay? Very similar to the quiz type stuff. And a combination of different types of questions. So you can expect some multiple choice type questions. You can expect maybe fill in or potentially some descriptive types of questions. Nothing like a long essay or anything. So you won't have anything like that. I probably will have potentially a great circle question. So make sure that you have a calculator available to you. Okay. And then I think if you bring your material, your book, your lecture notes, a calculator, you should be good to go. Okay. And I don't usually, I mean, it takes most people, I've anywhere from an hour, hour and a half to maybe 2 hours, but most people are done typically in 2 hours. So we should be able to finish that early. If you are doing it remotely, I will be sending that out via Blackboard. I will open that test up on Friday, and you'll have the whole weekend to do it. So it'll probably be open for like 4 hours. I always give people extra time when they're doing it online so that you have time to go through it and feel comfortable with it. So that's kind of how we'll be looking at that. Okay. So let me open this up to questions specifically, any topic or anything else about the test that I haven't covered. And I know I'm behind with you guys. I apologize for that with stuff. I'm really working hard on this classes, but I've got a lot of classes that are just like burying me. And like today, I have a lecture here in the morning, then I run over to the college, and then I come back and do this lecture. So my days are just really full. So again, no excuse, but that's just kind of what's going on with me. But I should get caught up this weekend with everything. So let me go ahead and open this up to questions, and we can review. I've got all of the slides up here, so we can look at any chapter. So the first chapter is just somewhat introductory stuff. The second chapter got into a little bit more meat where we were talking about map projections, those kind of things. Third chapter was dealing with realigning types of data sets. And the fourth one was GPS type of stuff. So let's see if anybody have any questions on anything. I'm going to open that up to you guys.
Are we going to have to do any of these coordinate transformations or anything like that?
Oh, absolutely not. If we didn't do anything like that, Ben, you're not going to be doing that by hand. The only thing I may ask you to do is a great circle calculation. Okay. So,
okay.
yeah,
Just
absolutely.
Sure.
Yeah, this is not a rigorous mathematical type class. Okay. It's more of an informational overview kind of thing where we're just getting, it's really more heavily terminology based and those kind of things than it would be mathematical. We're going to really use that very limited. Okay. So yes, definitely not anything like that. But, make sure you have a calculator for potential great circle, because that could be on there. Okay. So that's a good question. Yeah. Okay. Anybody else? Questions about the test? Specifics, format, timing? Not hearing anybody, so I'm assuming that we're good. Kim, do you have a question?
Not at all.
Okay. Anybody else? Would you like to look at any of the course material sections, like out of chapter 1, 2, 3, or 4 specifically? There was a lot in chapter 2, so I just want to make, I mean, we can go through any of those issues. I'm not trying to make this, in and out kind of session. So I want to make sure that we cover things. Okay.
I think I did. I did get one of the questions wrong on the quiz. What was the location-based? This location-based data has to
Oh
have
yeah,
a
yeah,
location
yeah.
associated with it.
Right. A lot of people did, and that question, if I recall, had to do with one of the answers was if you were given like certain things, what's considered like what's considered location based and spatial, non-spatial kind of data. And
Yeah.
I think one of the answers was they gave you a list of addresses. Okay. And a lot of people said, well, yeah, that's location based. But the reality is that just a list of addresses in and of themselves would be more considered attribute data. Because if you think about it, let's say the address is 220 Washington Avenue. I mean, think about how many places in the world that could actually be, particularly in this country. There's probably a 220 Washington Avenue in just about every major city in this country. So in and of itself, that's not really a locational based data. Okay, that would be considered what they call attribute data. And we'll be talking a lot about that as we get into chapter 5 and 6 and 7 as we get into the GIS piece. Okay, does that make sense now?
What was the correct answer?
I don't have the, let me see if I can dig that up. Hold on.
I think the correct answer was,
You have it?
I think it's parcel database of all residential developments in a neighborhood.
Right, that's correct. And the parcel information is information that's got, it's got potentially state plan coordinate, it's got bearing and distance, it's got stuff that ties it down to the earth. Okay. So you have to kind of read that pretty heavily to get into that, okay, to get to that point. But again, when you're looking at those multiple choice, you're kind of looking at what is you may have two answers that seem to be correct, but you got to look at the one that's the most correct. But in that case, the parcel would have been the most correct. Okay. Does that make sense now?
Mm-hmm.
Okay.
Yep.
So yeah, keep that. I mean, we did use that term. We started to talk about spatial versus non-spatial. That's a good introduction to what we're going to be getting into chapter 5, 6, and 7, and 8, because they're going to talk a lot about that. GIS is really big on that. Of course, that's not stuff that this test is concerning, but just in and of itself, just a list of addresses or something does not qualify as what you would call spatial data typically. It's just going to be attribute data. Okay. Yeah, that's a really good point. Really good point.
Which quiz was that question on?
That was on chat quiz 1.
Okay.
Yeah, that was on quiz 1. So quiz 1, let me see if I can pull this up real quick. Let's just we'll look at the topics here, and maybe the topics here will give you some kind of idea of what you might want to review here a minute. Let me pull this up real quick if I get this going. Let's see, from Geospatial Lab. Okay, here we go. So this is kind of what this first chapter was. It's just kind of an introduction, what is geospatial technology, kind of who uses it. So where we get to this geospatial data, that's kind of where that was kind of talking about coming from. So that would have been that thing. So do you want to look at any of these aspects here in this section? Or should we move on? Let's see if I can go down to that section. Here we go, geospatial data. Okay, so here Here's really what that was addressing. Geospatial data, or what's just typically called spatial data, it's location based. Okay. And what you can say about this is knows where something is located. So some things are going to have what we call spatial dimension. We're going to talk about this, guys, by the way, quite a bit, spatial dimension concept. And I think I mentioned that in the first lecture when we did this, but point location is considered 0-dimensional, length is 1-dimensional, area is 2-dimensional, and volumetric is 3-dimensional. They call that dimensionality when you get into the GIS concept. So we're going to see this same kind of thing again, but that's where that's coming from. Let's see if it's got a secondary. Okay, here's non-spatial data. So it's not location based. It can be linked to spatial data. In fact, if it's not, it's really truly worthless from the standpoint of using it in a GIS or for the kind of stuff that we would be talking about. It knows what something is. So example of a property owner's name, value, zoning, land use, okay? All right, so that's kind of addressing that issue. All right, anybody, anything else from chapter 1 they might want to talk about? We talked about that national map concept. We kind of looked at that. National map viewer, geography and how that relates. So this was really introductory stuff. Wasn't really too involved. Anybody see anything or think of anything on that chapter 1? All right, if not, how about I'm going to move to chapter 2 and then see if that oh, question?
No, not at the moment.
Okay, all right. I thought I heard somebody get a question. So I'm going to go to chapter 2. Let's take a look at this. So this one was a little meatier. It had a lot more stuff that actually pertains to, you know, our profession specifically. And so one of the things we were looking at here was datums, geographic coordinate system, how you can do translation, and UTM coordinate system, and state plane coordinate system. So those were the major kind of talking points in here. So does anybody see anything here that you'd like to talk about? You guys are pretty good with datum, what a datum is. What are the 2 major datums we have out there?
The NAT 83 and the NAVD 88.
Right, so basically you're talking about a horizontal and a vertical datum, right? And so the new one that's coming around in 2022 is basically going to be all linked into one. So that's going to be a big kind of a difference is what's going to be happening there.
So could you say a datum is a point of reference, or more of a point of reference or a surface of reference? And then
that's exactly what it is. It is basically just a reference that you reference other, or a thing that you reference other things to, okay? And specifically, let me see if I can get to that point. So there's just a set of quantities as a basis to calculate other quantities. Yeah. So, you know, we can use lots of different types of datums. We have local datums, you know, like for instance, construction people, a lot of times they don't really care where they are tied to the earth, but they do care where they're tied to a building. So you may have a floor grid that's your datum, and the corner of that floor is your vertical benchmark, because everything has to fit within the steel framework and, you know, be referenced to that. So we don't really care where we are at sea level necessarily. So datums can be, you know, they can be broad scope or they can be localized. And we use both as surveyors. I mean, when you guys, a lot of people, when they go out and survey, I mean, they're not tied down. You know, if I'm running a traverse, I'm just turning angles and shooting distances or whatever. And when I go into the office, I'll probably call that point 5,000, 5,000. I can always reference that into something later, but I can certainly stay in that localized datum if I need to. Okay. So yeah, that's a good question also. Okay. So I'll tell you what, I'm gonna maybe just go back here. We can kind of go over here. You can see some of this. If something pops up here, let me know if there's anything you'd like to talk about. Horizontal vertical control. You guys are good with ellipsoid and geoid? Everybody okay with that? This is a nice schematic of kind of how they work with each other. It's very schematic, but remember your ellipsoid is your mathematical model. The geoid is the equipotential surface, and then you have the Earth itself, which is, this crust is constantly moving and it's changing. It's uplifting, it's going down, but this guy, the ellipsoid's not moving because it's mathematical, it's Earth-centered, it's Earth-fixed. But the geoid's going to tend to change with what the Earth is doing. Okay, so it can be end shift as well. So if you see something, okay, just let me know. We'll talk about it. These are the current systems right now. Is it a true statement to say that WGS 84 and the GRS 80s are the same ellipsoids? You guys remember?
Yes.
You're saying that, yes, they are the same?
I don't believe they are the same. They're all very little, but they are very close to one another.
Well,
Weren't they the same at the start? And
they
then
were the same at the start, right, basically? But you can see even the parameters A and B, but over time, they've drifted apart. So actually, there's a bit more of a change between this one. So the GRS 80 is drifted, or well, actually the WGS, because it follows. So yeah, they've drifted apart quite a bit. So when you hear people will say this very often, oh yeah, they're the same ellipsoid. Well, they were at one time, but they're not any longer. Okay, so that's an important distinction. Okay, orthometric height. You guys okay with that? Geoid height differences? You okay with that? Let's go this way. Let's see. This is going to be pretty much obsolete. I don't know if you guys, did any of you guys have a chance to read that thing I put out there about Meads Ranch? There's that little article.
Yes.
That's a really good article. It was very interesting if you had a chance to read it. Of course, you're not going to be responsive. There's going to be no questions from those articles. But I do think they're really good to kind of focus in on. Let's see. So this is just, so I'm just gonna buzz through this, and if you guys have any questions, I certainly will talk about anything. The vertical datum, data transformation is a way of getting from one datum system to another. So we said that there's a collection of tools you could use to do a lot of this, right? Does anybody remember where you'd find that?
NGS website.
Yep, it's called the Geodetic Toolkit, and you can go in there and grab all that stuff. It's just really cool the way they've just
NADCON and VertCon.
What's that?
NADCON and VertCon.
Yeah, those are little sub programs in what they call the Geodetic Toolkit. Correct. Yeah. Yep. And yeah, and in fact, most of your softwares incorporate those into them now too. You know, like your GIS softwares and like things like Civil 3D, they have that capability as well. I think they just basically are using those programs essentially because the NGS they're the guys that wrote all that stuff. So they're the ones that are keeping track of that. Okay, let's see. Geographic coordinate system. Another name for that would be latitude, longitude. Okay, so when you hear that term, that's what you're talking about. Spherical coordinates, latitude and longitude. All right, so, you know, anybody see anything? Like I said, I'm not trying to hold you guys up, but I don't want to, you know, not talk about something if there's an issue. So let's see. International date line would be what?
180 degrees.
It should be, right? Theoretically, in theory.
Right.
And that would be west 180 and east 180, right? Because you're going to go both directions from the prime. But the reality is it meanders. If you look at this, that hard red line right there, that's actually the international date line. So you can see how it jigs and jogs around over here on both sides of that. So time zones, of course, they kind of do the same thing. All right, let's see. There's your, if you haven't done the great circle, there's your great circle issue. All right, that brings us up to projections. Map projections. We talked about a lot of the different types.
If you go back to the great circle, I do have a question on that.
Yep, sure. We're there. Okay. Let me bring that up for you, okay?
Okay.
There you go. All right.
Yeah. Down at the bottom where it says the D times 69.2 mile.
Right.
I'm not really sure what that D represents.
D is this angle. Okay. So D is the angle. See, if you take
Okay, so you take the arc cosine then of
correct.
Of that angle, and what you get would be times 69.2. Okay.
Correct. That's exactly right.
Okay.
So yeah, this relationship is just giving you the sine of D. So to get D in terms of a degree, take the arc cosine of what you get, and then that's that. So if you got a circular curve like on a highway, this is essentially delta, okay, is what that really is. So it's the greater the delta angle is, the farther the distance. And what they're saying here, what this is really saying is that it's 69 miles per 1 degree. You don't see the degrees here. So if you take 69.2 miles per 1 degree times degrees, degrees in the top and the bottom cancel out, and you're left in miles. Okay, does that make sense?
Well, yes, but when I was doing this, as an example, between what was it, Orlando and Seattle?
Yeah, something like that, right? Yeah.
And I took the delta angle times 69.2 miles, and it did not come anywhere close to what it should be.
Okay, so
and I really wasn't sure, so I just went into, okay, I know what delta is, and I know what the radius is, so I did it just the mathematical way of doing it. Didn't take it times the 69.2, and I came up with an answer that was logical.
Okay, so probably what happened is you somehow are in this equation, it's wrong, because that D angle, usually you hit it within, I don't know, within 10 miles of what you would see if you would list it, So it's going to be pretty close. Just remember, this is not a perfect equation, and there's also a lot of other ways of doing it.
Yeah, well, when I did it, I went into one of the programs, and it gave me what the great circle distance was, and I was within 5 miles.
Okay.
With what I was. So the way I calculated it was correct.
Okay.
But I could not get it utilizing that formula, and I just don't know why.
Okay. Well, you're talking about this formula right here, sine times
No,
sine?
the bottom underneath well.
Oh, this guy here.
But yeah, okay. I came up with the delta, but the delta. Okay, I mean, even if it was a 360 degree delta, try taking 360 times 69 miles, isn't going to be anywhere close to what the actual distance was.
Right.
360 times 69.
Yeah, you're getting a full circle around, right? If you do that, right?
Oh, yeah, okay, but well, that would be.
Right, that wouldn't make sense even.
Well, maybe I just hit something wrong on my calculator.
Well, I think that's what I was getting at. I believe it's probably in here somewhere.
Well, no, I got the correct D.
Oh, you did? Okay.
The cosine D, because I got the D correct.
Okay.
Because I utilized that in just the spherical formula.
I see. Okay.
2 pi r
Okay.
formula, and I came up with the right answer.
Hmm.
So I must have just hit the wrong button on my calculator when I went by b times 69.2.
Yeah, that's possible. That's possible. Okay. All right. Just so we're clear on it. Okay. Just want to make
Yeah.
sure.
Okay. Yeah, I got the right answer. Just okay.
But a lot of people, when they run this number, they always get it wrong the first couple of times. You got to really be careful. I have to do this too. You just got to make sure what you're doing with these when you hear. And sometimes this screws people up because this is the absolute value of the difference between your longitudes. So, yeah, you got to watch it. But other than that, yeah, it's pretty straightforward. Okay. Does that make sense now?
Yep.
Okay, cool. All right. Let's see. We talked about the map projection stuff. The pretty much 3 types of surfaces would be cylindrical, conical, and the azimuthal. And what they're indicating here are tangent planes, but really mostly be secant. So you're actually piercing that typically twice instead of just the once right here. Anybody remember the name of that line right there? Or right there on the cylindrical or the conical? Can you see my pointer, by the way?
Yes.
Okay.
But no,
Yes.
I can't
Okay,
remember.
this is called a standard line right here. Standard line. So what's happening there? Does anybody tell me what that means?
Well, that's where there's zero error or projection error.
Well,
Projection
yeah, okay.
error.
It's a zero difference between the distance on the ground and the distance on the ellipse on the projection, right? But what we usually say is that the scale factor there is 1. So usually you multiply your ellipsoid distance times a factor to bring it to the grid or vice versa. So here it's 1 to 1. Okay. So, and then outside of that, it's going to either be less than 1 or greater than 1. So
What
depending
did you
on
call
how,
that again?
this is called your standard line.
Oh.
Standard line. I think we got it down. Here it is. Standard line is the line where the projection surface intersects your ellipsoid. Now, if you're doing a true secant projection, you're going to have 2 standard lines, not just 1. I drew you guys a little diagram. We can do that again real quick. If you kind of look at this, let me see if I can draw this real quick.
I just don't think I added the term standard line
Oh,
to my
okay.
notes.
Okay. Well, that's cool. Well, we'll do this real quick. Come on. Maybe not real quick. Doesn't seem to want to cooperate with me today. All right. Why is that not? Let me try that with this one. I can't get it to draw it for me. Well, I'll just draw something.
Is it a color issue?
No, I don't think so. You know what it is? Let's see. I think it's, I don't know. I was using this earlier today and it was no problem. Of course, it doesn't want to work now. It could be a color issue, I suppose.
I mean, yeah, it could be white.
It's black. I don't know what's going on with this now. Let me try getting out of there and trying it again. Yeah, we used this earlier today and it was fine. Oh, you know what? Hold on a minute. Sometimes if I did this pen. Of course, this isn't going to work for me now, is it? Yeah, it's not a color issue. Clear. I'm going to close this a minute, see if I can open it back up. Let me see if I can do it. That little program is actually pretty cool. That's an Autodesk program. There we go. All right, I think I got it working. All right, so let's try this now. So if we have, there's my ellipsoid. And if we take a secant plane, now we're only looking at this two-dimensionally, right? So you got to envision that. So here's my projection surface. You might remember I did this the other day. Right here and right here, this is where you've got unity going on. So now you can't see this, but if this line was coming towards you here and coming towards you here, if you're measuring on the ellipsoid and you're measuring on the projection surface, the distance is going to be one and the same. But if you're up here at A and you're here at B, when this projects down to the projection surface, you get what we call A prime and B prime. So you notice the distance A prime B prime is less than the AB distance. So we say that the scale factor here is less than 1. I got that reversed, don't I? Scale factor is less than 1. So in other words, you go from 1 to less than 1 and back to 1. And then when you're out here, if you're on your ellipsoid there at C and here at D, when those project out, you get C prime and D prime. And here the scale factor is greater than 1. So you got 1, greater than 1, and less than 1. And the majority of your projection is right in here, okay, when they do. It's particularly like state plane. So that's what that's talking about. So that's the standard fail, and that's what we're seeing right here. That's that right there is what I was just talking about. So your scale factor is along the standard lines, 1, greater than 1 outside, less than 1 between. Conformality is the property that allows angles to be the same. Really what's happening is the shape is the same. So if the shape is the same, then angles are the same. But what does distort is distance. And saying that the angle is the same is not 100% true. It distorts a little bit, but for a small area, it pretty much stays pretty much stays true. Yeah. All right, so if anybody sees anything, let me know. Lambert, we talked about the Lambert conic conformal projection. Again, I didn't, there's more here than is in the book. I'm not going to go too much in depth on the test, but if it's in here, I mean, make sure you have these and you read them, okay, so that you understand. So let's see. UTM is a good thing to know about, the Universal Transverse Mercator System. It's a worldwide system, and it goes from, 80 to 84, I believe, 80 south to 84 north. And then you have the different types of systems, the stereographic projections up there. And these are zones that are broken down into 6 degrees of longitude wide. They start at the international date line, and they work towards the east. Okay, so let's see. I think we covered this pretty well. So if there's anybody have a question, let me know, okay? And then state plane, again, we didn't go real in depth on this, but I did try to give you some of the highlights. What are the 2 major state plane systems that are used?
Lambert
Yep.
and the transverse Mercator.
Correct. And this map is really nice to show you that. It doesn't show you what zone's what. You kind of have to know that. But if we look at this, Ohio is a classic Lambert state. Well, actually, Tennessee is a classic Lambert state. Any state that tends to be long in an east-west direction is going to use Lambert. and any ones that's classically long in a north-south direction is transverse Mercator. So Indiana, Illinois, those are transverse Mercators. Ohio, we're Lambert. Kentucky's Lambert. Tennessee's Lambert. And Lambert, really, from a calculation standpoint, is a bit easier than transverse Mercator. Transverse Mercator is pretty involved. And you also notice, remember what the original range was? So to keep your scale factors to a minimum so that you didn't have distortions as much. Anybody remember the original distance?
158 miles.
Correct. Okay. So notice Montana greatly exceeds that. But what happened, so does Nebraska, and so does South Carolina, I believe. So those guys, when they went from the 27 datum into 83, NGS really approached the states and said, if you want to go to a single projection, we can do that. So these guys opted out of multiple projections. So these guys have a little bit more distortion associated with them. One of the things I think I also mentioned was Kentucky was to a north and a south at one time. About 10 years back, they decided they wanted to go to a single zone. So they basically now have a single projection. Although I think you might find coordinates really in 3 forms now. So you could have a north-south projection, and then you could also have a single zone projection. But I'm sure that they're probably going to get rid of the north-south entirely when they go to the 2022 kind of thing. So yeah, this is a good little chart. Okay.
Is it true
yeah,
that
that's kind of,
is it true with the 2022 system they're going to go to more county-based zones?
Or
how's that going to work?
I'm not really sure about that.
That's what someone else was telling me.
That's a good question.
It's going to be more. It's going to be super local now.
Mm-hmm. Well, a lot of people are kind of already using that, and the reason they're doing that is because they're minimizing distortions, obviously. A lot of people have actually been using what they call a local projection for years. And I'm not sure how the NGS is going to handle that, but I actually work on a committee for the surveying ASCE group. And one of the guys that's on that committee is a guy by the name of Michael Dennis. And he's like the head of the NGS. And he's like the state plane coordinate guy. I mean, he's written all of the language to the new laws that are coming in. So if I get a chance, maybe I could talk to him, see. Really knowledgeable. It was pretty interesting when I found that he was on that committee. I was like, wow, he's the guy that's writing all the stuff about that, and he works for them. So, but yeah, I don't really know the question. I'd have to look into that. But there's plenty. If you go out to the NGS webpage, there's a whole section on the new datum and how that's going to work and everything. I'm probably guilty of not reading it as like I say to you guys, yeah, you'd probably be reading that. I should be too. So we all should start checking into it because it's going to be here before we know it for sure. So that's a good question. Good question. I just don't have the answer, but it wouldn't surprise me because local projections are becoming a thing. There's been a lot of papers out about that. If you've read some of the things in POB and Professional Surveyor, there was one article a couple years back about that very concept. So that's a good thing. All right, anybody, anything else here you can think of? All right, I'll go ahead and close that one. Minimize that. So let's see.
Are you going to cover all those symbology having to do with the state plane coordinate system that you were showing?
Absolutely not. I mean,
okay, because
first of all, we didn't go into it. Okay, so really anything, a lot of that for you is informational. Now, I'll say this: you should know 2 symbols. Okay, you guys all need to know this symbol. I mean, you need to know this symbol and you need to know that symbol. That's fair game. So what is this?
Latitude.
That's latitude.
Latitude and longitude.
Correct. Okay. So that's phi and lambda. Everybody should know that. Okay. That would be about the extent of it, Ben. Okay.
Okay.
But
I always
I'm
get
not going
those
to have,
mixed up too.
I'm not going to have anything specific about that. And I'm not, this is not a test about trickery. Okay. It's not that. It's just general knowledge. Okay. So if you've read the stuff and you've gone through the lecture pieces, you should be good. That doesn't mean you may have to look some stuff up, but you'll have the availability to look that up. So like I said, make sure you bring your text. Okay. Yeah. But yeah, these two really should, you guys should all memorize that, because those are very common symbols that we use in location. Yeah, definitely. Right. Right. Anything out of this section? I didn't have a chance to really do a lecture on this, but most of it was straight out of the book reading. I think it was pretty straightforward, but we can look through there. This was basically talking about getting things to georeference, okay? The concept of georeferencing and kind of what that is. And that's pretty straightforward stuff, really. But that's I love that picture, because it really shows the difference between what you're doing with a map projection of Lambert and what you're doing with Mercator. Picking that as the point of projection, how they really come unglued the further you get away in one direction or the other. Yeah. Let's see. Trying to see if there's anything. You should understand that that's a good term, georeferencing, where you're aligning unrelated data sets. That's a really important term. Let's see. The concept of control points, where a control point would be a point on either a good map like Google Earth or the Earth that you know, and one that you can reference on a picture of some kind so you can correlate them. Those are important. And what makes good control points and what makes bad control points. So we talked about kind of this picture. I'll pull this guy up real quick. Okay, so this was that map that you guys actually used. And this is the same location in Google Earth, which you also used. And bringing those things together using the process of placing control points. You have to have the same point, obviously, on both data sets. And you're going to need real world coordinates. So in this case, what that program was doing, you were picking points on here and it was generating a real world latitude and longitude of that position. And then, let's see, whoops. They should be spread out throughout the site. That should make sense. You don't want 3 points that are real close together. That's not going to work very well. And 3 is an absolute minimum. Okay, those kind of things are pretty straightforward. And this picture was showing you good and bad. So your author's basically saying that's a good point, that's a good point, that's a good point. That's probably not a really great point. That's not a great point. Okay, so I mean I think you got the idea. This stuff wasn't that big of a deal. Okay, so let's see. Transformation types, or what happens in a piece of unreferenced data. You got the 4 things that potentially could happen: rotation, skewing, scaling, and translation. Translation just means moving. And I think I mentioned if you were using AutoCAD can't do one of those.
Skewed.
Yes, correct, right. So that was something that you can't really do with AutoCAD, but you definitely rotate, scale, and translate. In fact, the command called align, if you've never used that, that's a super tool in AutoCAD. Yeah. Okay. Yeah, I mean, let's see. I think that's all pretty straightforward stuff. Any transformation program usually calculates what's called a root mean square error, which identifies how close you think you are, it thinks you are to the actual point and what it calculated. So the lower the number, the better, or the higher the number, the better?
Lower.
Lower, right. So what you want to do, if we look at this, they're calling them residuals here, but the lower the better, okay? So I don't even know if those are meters or feet, but, or they could even be, who knows, centimeter. I doubt that. But so yeah, we're looking at, that one's not the greatest point. And if you scrolled in this we can't do that, but if you scrolled through that, they probably have a bunch of other points in there. And I'm assuming well, that's just ID number, but it could be as you go down this list, they're getting even worse. But that doesn't look like that's the case because that one's higher than that. So it's probably truly just whatever number you got looking at there. And I think I told, this program is what's called a DREASY. We used to use that program at the college. It's a GIS package actually. And it was pretty cool, but we don't use that anymore. Not too many people use that. So, okay, so that was chapter 3. Any questions on that? Anything? Think of that. Like I said, that one's probably one of the most straightforward chapters we've looked at, I think. Okay. All right, so let's go to chapter 4, which was the stuff we did last week, and that was dealing with the GPS stuff. So my lecture notes are probably a little bit more in depth in the book if you read the book. I mean, everything I talked about is in there. Some of it's right the same, but we talked about some other things that the author didn't. But I think we covered that pretty in depth also. So does anybody have any questions on that? You guys are too easy.
I don't think so. That's just a lot of.
Oh, you're just too good.
Yeah. I'd like to think that, right? Right. Well, we'll see how good we are Friday or Thursday. I think you guys won't have any problems. But just, reading the chapters is good. If you've had a chance to go through them, maybe just buzz through them again. Make sure you have this stuff handy. And I think we'll be good to go. And then next week we'll start into chapter 5. I will say this, that probably chapter 5 is going to be quite a bit different for most of you, because unless you have a lot of GIS background or experience, you're going to get a lot of terms there that are different, but they're going to be good for you guys to understand and hear, because there's, in our, we deal with that kind of data a lot. I might have mentioned this, but I talked to one of the other students that I've had he just recently took the fundamentals test, and he said a whole lot of those questions on the fundamentals were right out of more GIS based than other types of things. So he was a little bit surprised. But of course they randomized the questions, so you might go one time and it's maybe more another way of questions. But you definitely have to have that background when you take that test. So I think that the stuff in chapter 5, 6, 7, and 8 will be really, really good as an introduction. But we're not going to get into it like super in depth. All right. So does anybody have any questions? Because if not, I don't really have anything more to go over too much. I'm going to go ahead and pause